We introduce AdaNeRF, a compact dual network neural radiance field that can be trained end-to-end and adaptively sampled in real time. The core of AdaNeRF is a sampling network which is evaluated only once per few array and predicts the importance of all sample points along the array. By thresholding the importance, we reduce the number of samples evaluated by the shading network, which is run once for each sample. Relying on accumulation along the array, we can set up an end-to-end training scheme. AdaNeRF is the first neural rendering method that enables different sample counts for each individual array without an additional data structure, placing samples where they are most needed. In this visualization of our four-phase training scheme, we show the outputs of a single array for both the sampling network and the shading network on the left side, and the resulting output image on the right side. First, in the initial dense training phase, the shading network is sampling the full input space to provide an initial estimate of the scene, as the sampling network outputs are forced to be 1. Second, the sparsification phase slowly forces the sampling network outputs towards 0, while keeping only the most important samples active. This distills the knowledge of the scene from the densely sampled shading network to the single evaluation sampling network. Third, we freeze the sampling network and allow the shading network to adjust to the now sparse sampling network, as samples are now deactivated according to the sampling network outputs. Finally, with both networks being trained, we can additionally fine-tune the shading network on a specific average sample count by thresholding the outputs of the sampling network. Due to being extremely compact, we can split a large complex scene into multiple AdaNeRFs and interleave outputs of at most 2 AdaNeRFs at the same time. This enables high-quality real-time rendering with intricate visual phenomena such as reflections, while still consuming less memory than competing baking or caching-based approaches. Note that even novel views outside the training distribution can lead to satisfactory results. We now compare against other sampling reduction methods, focusing on equal speed comparisons where sample counts can be tuned. The pavilion scene is especially difficult because it includes a transparent water surface, reflections, and fine geometric detail. DoNeRF is quite blurry at the water surfaces and distorts the geometric detail. TermiNeRF misses out on view-dependent effects and has issues with the sky and other areas which are only present in few views. Although Planoxels uses 100 times more memory than AdaNeRF, it is still relatively blurry and also shows floating artifacts for areas which are only present in a low number of views. The classroom dataset includes many sharp geometric features where DoNeRF tends to create artifacts. In these cases, AdaNeRF reduces quality more gracefully as it can place more samples around these difficult areas due to its adaptive sampling scheme. TermiNeRF shows even more issues around those areas and it is not able to faithfully reconstruct good depth estimates. Planoxels again tends to blur out features like the textures on the chairs or the writing on the blackboard. The flower dataset again highlights that AdaNeRF is able to place more samples around depth discontinuities, leading to fewer artifacts compared to DoNeRF. The same is true when comparing against TermiNeRF, where black holes also appear at the thin leaf structures. While Planoxels requires only 30 times more memory than AdaNeRF to represent this dataset, it again creates an overall slightly blurry output. The Fortress dataset is challenging due to its repetitive structures, making it more difficult to learn the real scene depths. At an equal speed, DoNeRF shows significant sampling artifacts with holes and halos, whereas AdaNeRF only shows few artifacts on the left side of the fortress. TermiNeRF additionally fails to shade the fortress structures properly, likely due to suboptimal sample placements. Planoxels shows hardly any artifacts, but is significantly more blurry than AdaNeRF. With our real-time viewer, AdaNeRF scenes can be explored interactively. Please note that the artifacts here are due to out-of-view cell imaginations. In summary, AdaNeRF is a compact, real-time, dual-network neural representation that can be trained fully end-to-end via a soft student-teacher optimization scheme. It is the first of its kind to adaptively place a very low amount of samples for each individual view ray, outperforming previous work in quality, compactness, and rendering speed.